Welcome back. So far in this course, we have trained a lot of machine learning models and predicted molecular properties. The machine learning concept in was envisioned way back in 1950s, but what really sped up the AI revolution nowadays is the use of GPU and the architecture to run it. And these GPUs speed up the calculation a lot. And if we compare the speed on a CPU, it's around 10 times faster to run it on GPUs, and that's why we see a lot of machine learning models nowadays. And in this lesson, we'll see how to use GPUs to speed up machine learning property prediction on molecules. So what we'll do over here is use the graph neural network model that we discussed a while ago and train the model on GPU. If you remember, the graph neural network on 5 epochs took about 5 minutes or so to train the model. And that was a fraction of a model, that not the entire dataset, but around 5% of the QM9 dataset. And let's see how that fares when we use the GPUs. So at first, to use GPU in Google Colab, you need to go to runtime and change the runtime type. By default, no hardware accelerators are used, but you can use the GPUs. And if you are using the free version, you'll have the T4, but if you have paid version, you'll have access to this better performance GPUs. But T4 is good enough for preliminary purpose. So we'll save this, and you'll see it's reconnecting. And once it's reconnected, you can see it's reconnected. Once it's reconnected, it's initializing, and once it's reconnected, you see that the connection is to backend GPU. You can see that GPU in the bracket over there. So that means we are using GPU for training. And let's install the packages for the code that are needed. In this case, we are using the DGL as before, and note that we are using something that is dependent on CUDA and not just DGL. And sometimes the packages nowadays are dependent on specific libraries, so just check the documentation page and make sure that you have the correct versions of the package installed for the purpose. So let's install this package over here. Once it's installed, we have all the necessary things for using GPUs, and the next part would be looking at the QM9 dataset and the HOMO-LUMO gap as before. So the code in this cell that you see is copied from all the previous notebooks that we looked at. The first step would be reading in the CSV file and then creating a data set, and again using 5% of the sample. And once that is done, let me just run this. We can featureize it. Because we are using graph, we use a graph featureizer with atoms and bonds, and apply the featureizer on the entire dataset to get the graphs. And once that is done, we split it into test, train, and valid dataset. We need to convert the dataset into a data loader so that it's easy for training. So we have the collate function, which maps the graphs and y's, the prediction values, which are the HOMO-LUMO gap in this case, and we create a batch graph, and we have the loader, the train loader, test loader, and validation loader with batch size of 64. All of this is the same, just copy pasting of the code before, and we have the MPNN model with the MSE loss function and the optimizer. So far it's the same code. There's no change when you use GPU in this part of the code. What changes is where we have the training and testing or validation loops. So that code over here is what we need to change. And by default, all the tensors or models that you create are residing on the CPU. So we need to transfer them onto GPU, then do the computation. So at first we'll transfer the model to the CPU, and this is how you would call it. So you use the model.to function and pass in the device parameter as CUDA0, and CUDA is the library that we are using to interact with the GPU. So it's CUDA0. This is one place that you need to change. And now remember that the model over here is on GPU, so all of these things should also be on GPU, or else it'll complain that it's not on the GPU or some different device. So we'll do batch.to device and return it to a batch graph. And you can notice the difference in the syntax over here. Earlier for the model we just did model.to, and that works only for the models, but when you use a tensor or any other thing, you'll have a return value, so make sure you save it to the return value as batch graphs. So we do it for edge and edge nodes. The prediction over here is again on GPU, because the model is on GPU, everything else with the parameters for the model are on GPU, so the output is in GPU. So that's the reason we also need the target values on the GPU. So we do the transfer to the GPU for each batch that comes in, and that's how the code for the training and testing changes. So once it's done over here, we need to do same thing for the validation as well. We have torch with no grad. The model is already on GPU, so we just need to change these parts to CUDA, and that's all. This is the only change that you would end up doing to convert the training process to a GPU. So let's see how fast this is. If you recollect, this model when trained on CPU took about 5 minutes to run this code, and we still had 5 epochs in there. And let's see how fast this code is, and let's start it. You can see the time here at the bottom, which is like 5, 6, 7 seconds, 10 seconds, 11 seconds, 12. So we are at 22 seconds. It's already done 4 epochs, and 5th epoch is already there. And so we have, in 29 seconds we ran the same code that took about 5 minutes before. So we can see the amount of speed up when we use GPUs. And if you have any model that is taking a lot of time on CPUs, we always try to use GPUs for training these models, and that's why we have a lot of AI models, large AI models being trained pretty easily these days.